Hey calculus students, today I'm going to do my fifth lesson in derivative techniques unit. We're going to work on deriving logarithms, Euler's number, e to the x, and just all sorts of differentiation and such. So these things, differentiation of logs, Euler's, like e to the x, you may see those referred to as transcendental numbers, or most texts will talk about derivatives of transcendentals. That's what we're going to go over today. And starting off with, what's a logarithm? Well, it's the inverse of an exponential function. You say, well, what's an exponential? Here's an exponential. If I have like 2 to the power x, 1/3 to the power x. It's when you have some base raised to an unknown exponent, and let's just talk about that for a minute. So I'm going to go back and do a little pre-cal. Again, that's not the purpose of this lesson, but just to show you. So if I have the equation y equals 2 to the power x, I know anything to the power 0 is 1. So I know if I raise 2 to the 0, it gives me 1. So my graph will cross there. And since my base is greater than 1, this will give me exponential growth. So there is my exponential function. Now my logarithmic function be like log y equals log base bx. Now again, to be an inverse, remember you switch your x and your y. So instead of 0, 1, it will cross at 1, 0 and have that asymptotic behavior with the y-axis. And this is what your log function looks like. And just kind of a rough sketch. And if you draw, oh my gosh, better than that, I guess. If you draw better than that, if you draw the linear parent function y equals x, it should separate the two inverse functions by serving as their axis of symmetry or their line of symmetry. So that's kind of the relationship between an exponential y equals 2 to the x and a logarithmic function y equals log base 2 of x. So to really get an idea of what a logarithm is and what it does, I'm going to give you a log expression. So if I consider the expression log base 7 of 49, what it does not mean you're going to take 7 to the 49 and get something. Number one, that answer is really huge. And secondly, the answer to this is not really huge. It's quite small, actually. So what this means, or how this represents, is like this. It represents the exponent that your base of 7 needs to become 49. In other words, what power, so I have some unknown power that 7 needs to become 49. So instead of 7 to the power 49, which is really huge, it's 7 to the what is 49. So really, this is just one of the world's ugliest ways to say the number 2. Okay, natural logarithm. What is it? It is a log with a base of e. You might say, okay, that's cute. What's e? E is an irrational number, approximately 2.718281 and change. It's referred to as Euler's number. Similar to like pi, it does have uses. Again, I'm not going to go through that. Let your Algebra 2, your pre-cal teacher talk to you about that. I'm more interested in the calculus, but some properties of logs. Now, I know you've learned these probably in Algebra 2. I'm quite sure your pre-cal teacher would have went over them as well. I want to kind of help you understand them a little bit better. So to do that, I'm going to go back to this other page here that we're working on here, these other problems. And if you recall, when I'm doing a logarithm, what it helps me do is to find some exponent or some power. So basically, when I'm doing properties of logs, I'm really doing properties of exponents is what I'm doing. So let me show you, not just Here's a formula, memorize it. Now, that being said, I do want you to make sure you have these formulas memorized. They're going to come in real handy on your AP test, because I know that the College Board does like to use logs quite a bit, specifically the natural log. But we're going to actually use those properties quite a bit here to take some things that are ordinarily quite difficult and challenging and make them pretty simple. So let me explain where they come from. So again, logarithms, it's like finding an exponent. So get that relationship down. So when I talk about properties of logs, I'm talking about properties of exponents. So if I have like a to the power 3 times a squared, if you've passed algebra, I'm quite sure you'd know that that is the same as saying a to the 3 plus 2, or a to the 5th. So more important than the answer a to the 5th is what happened. Well, we added powers. That's what happened. So, all right. So we think about this and ask ourselves, when did we add powers? Well, when we were multiplying. Same thing here. Think of this log as like a power. This log like a power. What are we doing? We're adding those two powers. When did we do it? When we multiplied. So this property of logs is basically similarly tied to this property of exponents, in that one log being multiplied turns into two logs, or two powers, being added. With that same thought in mind, I have log base by. So here again, think of this like an exponent. I'm subtracting. So when would I take something like this? When would I take like x to the like 5 minus 2 power, which would be like x cubed? When do I do that? Well, that's when you're dividing. So when you're dividing, you subtract the powers. So when I'm dividing, I subtract the logs. Property 3. Another little property you may know. If I have, say, a to the power 2 raised to the power 7, hopefully you know that when you have a power raised to a power, that you actually multiply. So that would be a to the 14th. So here I have a power raised to a power. What happens when I raise a power to a power? Well, you multiply the powers. So I move that to the front and multiply. So that's where these three properties of logarithms come from, and we're going to use those quite a bit in this lesson. Okay, some basic formulas I would like you to know. I'm sure your calculus teacher would like you to know. The derivative with respect to x of ln x. I'm going to give you the definition of it right now. It's defined as 1 over x. I will do the proof for both this and for that the derivative with respect to x of e to the x is itself. I know in my class I have a little activity I like doing with them where I give them a graph and I'll have like a function. I'll have like 15, 16 different graphs of it, and then I have a graph of f prime. And again, e to the x is an exponential growth. It looks something like this. And then the f prime looks exactly like it. This freaked my kids out a ton, because I mean, some of the graphs were easy. You know, you have like an absolute value graph. Here at your sharp turn or your corner point, it's undefined. So you had negative slope, undefined, and then undefined positive. So those my class dealt with very nicely. And again, if you don't have something like that put together, it's a really neat activity. It really helps, at least I found it helps my students to do and understand the relationship between an f and an f prime graph. But this one freaked them out. They're saying, well, I did everything else, and the ones that are left over, they match up, and why is that, and can that even be? And well, basically, yeah, I mean, if you think about it, the slope here is really small, almost 0, which corresponds here, but all the slopes are positive, which here they are, my f primes, they're all above the axis. They're positive, and then increases in value, positive. So yeah, so if you're in my class and you did that activity and you're wondering why the one had the same f prime graph that it had for the f graph, that's because the function I gave you was actually e to the x, and e to the x is its own derivative. Another little properties of logs, I will probably prove this in a separate lesson, but this lesson is going to get really long if I go ahead and do that here too. But definitely we are going to prove these two and do some practice. Okay, so the basic idea here is this. When I'm deriving an e to some power and an ln of something, I like to think of them as chain rule type of problems. Like when I'm doing something simple like this, like derivative with respect to x of ln of x, I told you that that was 1 over x. Well, it's really not, because technically it's a chain rule where, like, this is my outer function f and this inner function g here. And if you remember your chain rule, when you derive an f of a g, it's f prime of g times g prime, like that. So technically, or if you do it in terms of stuff, when I derive, I guess I did not want to erase all of that. When I derive ln of x, I derive the ln, I derive my outer function, which gives me 1 over whatever. So that would be my f of, and then I plug in my g of x. And what I missed is the g prime. So what is the derivative of x? So technically the derivative of ln of x is 1 over x times 1, which is just 1 over x. But I think understanding that separate little chain rule factor here of 1, that you actually have to derive the inside or the stuff, I think that'll help. So I choose to think of it like this. It works pretty well for my kids, or it has in the past on their AP exams. When I'm deriving ln of something or ln of stuff, I basically just take 1 over my stuff, and then I multiply it by my stuff prime, which is really saying take f prime of g times your g prime, which is your chain rule. Now, if instead of writing it as 1 over stuff times stuff prime, if I put that over 1, you basically just get stuff prime over stuff. It's the same deal. Same idea with deriving e. We remember that the derivative with respect to x of e to the x, that's the one that the f looks like the f prime. So technically that would be like e to the stuff. You know, we leave it alone. But then I have to prime the stuff. The derivative of x is 1, so it's just e to the x times 1, or just e to the x. So when you're deriving e, it's e to the stuff. You know, you leave it alone. It's its own derivative. But then you have to multiply by your chain rule factor here, the derivative of your stuff. Pretty easy things to do. I'd say pretty easy stuff. Okay, poor joke, but start with some easy ones. Derivative of e to the 5x, again. Here's my stuff. So I take e to the stuff, which is e to the 5x. Then I multiply it by the prime of my stuff, or the derivative of 5x is just 5. Use your commutative property to move the coefficient 5 into the front, 5e to the 5x. E to the x squared, same deal. When you derive e to the stuff, and there's my stuff, the x squared, I get e to the stuff, or e to the x squared, times it. Whoa, wait a minute. Where'd the 2x come from? The prime of your stuff. Again, I like moving the 2x to the front, just habit. And I guess it's kind of habit because I know AP will probably write that like that on a multiple choice also. And then the last one, again, I take e to the stuff, leave it alone, times the stuff prime, and I get that as an answer right there. Now, if you want, and say the whole negative power thing just really irritates you, hopefully remember that when you raise something to a negative power, it makes its reciprocal. So In all actuality, if you felt the need to, you could actually write that as the negative 15x squared, which does not have a negative power, so it stays right where it's at, over e to the 5x cubed. Either of those answers works just fine. Okay. Practice a couple more here. Derive ln of, so we derive some e's, now let's derive ln. And again, remember I told you that when you're deriving ln of stuff with respect to x, you first derive your ln, which is 1 over something. In this case, it's 1 over your, whatever your stuff is. And then you do your chain rule factor, your stuff prime. And so that's going to give me 1 over the stuff. Yikes. 1 over the stuff, so it's 1 over the 7x. And then your chain rule factor times the derivative of 7x, which is 7, which gives you 7 over 7x, which reduces to 1 over x. You say, whoa, that's kind of cool, because the derivative with respect to x of ln of x was also 1 over x. So maybe you got this thing going on in your head that, like, hey, the derivative of any ln is just 1 over x. No, don't lose that right now. It's not true. This is a certain instance in which it is true, and really the only reason it is true is because my stuff here is linear like that. It's just a 7x, just nothing like that. So yeah, ln of 5x is probably going to be 1 over x. ln of 2x is like that, but if I take something nonlinear here, I think you're going to notice it's not 1 over x. So like this, for instance, you know, I got a sneaking suspicion we're not going to get 1 over x here. So I derive natural log of x cubed. So I take 1 over my stuff, 1 over x cubed, times the derivative of my stuff, which is 3x squared, which basically makes 3x squared. If I put that over 1, top times top, bottom times bottom. No, didn't want to show that yet. So that would be 3x squared over x cubed. Cancel 2 x's, 3 over x it is. So, no, the derivative of everything is not 1 over x if it's natural log. Take a nasty one here. Again, cosine x is my stuff. So hopefully you remember the derivative of your trig. So I take 1 over my stuff, or 1 over the cosine. Then I multiply it by the stuff prime. And yes, the derivative of cosine is negative sine. Now if I put that over 1, again, top times top, bottom times bottom, I get negative sine over cosine. And if you remember that as an identity teacher, as a trig identity, go thank your pre-cal teacher. Sine over cosine is really tangent. So we have negative 10. So that's your basic behind the derivatives of transcendentals. Yes, we can make it harder. We can throw in, you know, some advanced chain, some product, some quotient, whatever, but that's the basics. So rather than just taking my word for it that the derivative of e to the x is e to the x, I'd like to know for sure, like, where does that come from? So I'm going to do this. So I'm going to take this and I'm going to call it y. Now again, when I say to differentiate or to find the derivative, I'm looking for like a y prime equals something. That's what I want to get to. So I want to prime this. But before I do, I want to use those little, let me find those guys. There we are. Nope, not quite there. These guys right here. I love me some log properties. Specifically, I'm going to be using this one in a minute, where you have the power to a power and you multiply the powers. So let's go back to where we were here. Here we go. So I'm going to start with y equals e to the x. You say, well, you can't use the log properties because there's no ln's there. There is now. I'm going to take the natural log of both sides. And notice here, I have a power raised to a power. What do? I use my log property. That x moves to the front, you multiply the powers. Now, a couple of things that I think you should know that'll serve you well here. You should know what the ln of 1 is, and also what the value of ln of e is. Now, to show you what those are, remember ln just means a log with a base of e of 1. And then I'm going to call that something like, let me call that x, okay? Now, when I'm doing this, when I'm evaluating this, the e is my base. The 1 I call my answer. And then the x is my exponent. So I can rewrite log base e of 1 equals x, like saying the base e to the power x is 1. So to find this unknown power or this unknown value for ln of 1, I need to know what power I raise e, or like 2.718281 and change like that, that irrational number that's a little bit less than 3, where pi is an irrational number a little greater than 3. That'll come in handy later when you're doing geometric series in like a Cal BC class and convergence and stuff like that, but not so important right now. But anyway, what power do I raise anything to get 1? The answer is 0. So ultimately, what do I need you to know? I need you to know that ln of 1 is the same as saying 0. The other one I want you to know specifically for this problem is ln of e, because we need to find that. So ln e means I have a log base e of e equal some unknown power that you were trying to find. Okay? So again, I take my base, my answer, and my exponent. So e to what power stays e? Well, I know anything to the power 1 stays itself, so ln of e is 1. So really, this is just another way to say 1. So I simplify, and I get this. And then 1 times x is just x. Now again, I've done no calculus up to this point. All I've done is just a little algebra, use some log properties, try to simplify stuff down, and then we're good here. Now, to finish up, now we derive, and I'm going to derive implicitly. So I'm deriving with respect to x, and remember when you're deriving an ln, that's 1 over your stuff times your stuff prime. So that's going to give me 1 over y times my stuff prime, y prime. And then the derivative of your x is 1. Now again, we're looking to derive, which means, or differentiate, which means I want to get the y prime by itself. So I multiply both sides by y. Now that'll cancel with that y, so I just get 1 times y prime, or y prime equals 1 times y, which is y. So in other words, I know that the derivative of something is equal to the original function. So I'm going to go back, and way back at the beginning, what was it that I called y? Let's just see. Oh, I started with y equals e to the x. So then, if y is e to the x, then y prime is e to the x. So therefore, QED, quote erat demonstrantum, thus it is demonstrated, the derivative of e to the x is in fact itself. Okay, kind of cool. While we're at it, why don't we take on the proof of the other transcendental function here, derived with respect to x, ln of x. Again, I stated for you at the beginning that that's 1 over x. Don't take my word for it. Let's prove it. So to do that, I'm just going to take this right here, ln of x, and I'm going to call it y. Now, this already has an ln in it, but this time, you know what? I think I want to get rid of the ln, so I'm going to exponentiate both sides. Maybe your teacher refers to that as e-ing it. I don't know, but I'm going to call it exponentiating both sides. And when you take e to the ln of something, those inverses cancel out. So I'm going to be left with just e to the y equals x. Now, we already know how to derive e to the y because we just proved what the derivative of e to the x is and stuff. So it's e to the stuff times the stuff prime. So it's going to be e to the y times y prime, and then the derivative of x is 1. Again, to differentiate or to derive, I want the y prime by itself. So I'm going to divide by e to the y. Now let's go back a little bit, shall we? I know I've seen an e to the y somewhere. Oh, here it is right there. What does e to the y equal? Well, it equals x. So instead of my derivative equals 1 over e to the y, my derivative of ln x is 1 over x. Again, QED. Okay. I don't know about you, but for me, I like knowing where stuff comes from, and there's some really cool proofs you can do using natural logs to prove the derivative of the power rule, the product rule, the quotient rule. They're really cool. You know, maybe play with it, figure it out on your own, or ask your teacher about it. It's really kind of cool. So let's derive some harder ones, not just ln of 3x or ln of 2x. Let's throw in some nasty, stuff. So again, when I derive ln of stuff, I know that equals 1 over stuff times stuff prime. So I'm going to get 1 over my stuff, 1 over x squared plus 1, times stuff prime. And the derivative with respect to x of x squared plus 1 is just 2x. And if you wish to put that over 1, top times top, bottom times bottom, 2x over x squared plus 1. Game over, easy peasy. Okay, looks a little nastier, isn't? Oops, hang on. So, again, what am I going to do? Deriving ln is 1 over stuff. So I'm going to get 1 over 4x cubed minus 5x plus 3 times, what is the derivative of my stuff? So what is the derivative of that? Well, that would be, using your power rule, 12x squared minus 5. Put it over 1, top by top, bottom times bottom. I get 12x squared minus 5, 4x cubed minus 5x plus 3. Again, don't let deriving transcendentals freak you out. It's really not that bad of a deal. Even a calculus teacher can do it, so can't be that hard, right? Okay, now stuff's getting real. For those of you taking AP Calculus, don't freak out and say, nope, I'm dropping right now. This is not the kind of a problem that you're going to find on your AP test. This is just punitive, which makes it fun for me. So how do I deal with it? Well, a lot of you people, maybe you freaked out in Algebra 2. Oh, I don't like logs. I don't like ln's. They make life difficult. They are about to make this really, really easy. Because otherwise, think about it. You say, oh my God, I've got to derive ln's, and then I got multiplication, so it's product rule, and then I got dividend, so that's quotient rule, and I have square roots, so there's like chain rules, and it's just blech, you know. Just the sight of that's probably going to drive some people insane. It's not that big a deal. It's something we can handle if we use our log properties. And I can use my log properties because I have a natural log. Remember, when you're multiplying one log, I can write it as 2 logs being added. And then when I divide, that's subtracting some other log. So that's the steps I'm going to take in this. I'm going to actually use the log properties to break it down nice and neat for me. So again, 1 log with multiplication means 2 logs with addition. And then when you take a log with division, you subtract that 3rd log. So what we've been able to do is take this big conglomeration of just yuck and filth just sitting there and break it into smaller pieces that we can take apart and dismantle and then eventually derive. Again, I'm not ready to derive yet. What I like to do with my calculus when I'm doing differentiation, I like to do whatever algebra I can at the beginning to clean it up first. And then once I get it cleaned up and it's nice and it's friendly and nothing whatsoever like that, then it's a lot more friendly to derive. So that was using the first 2 log properties. You know, multiplying is adding 2 logs, dividing is subtracting logs. The other thing I want to do is, remember we talked about that 3rd property, when I have a power and a log x is a power raised to a power, that I can actually move the power to the front. We're going to do that here as well, only really remember the square root is like saying to the 1/2 power. So that one we're going to have to clean up a little bit more, but I hope it makes it kind of easy to follow what I'm doing here. So here, move the power to the front here. This one, square root is really the power 1/2. And then in our next step, we'll use that 3rd property of logarithms and move it to the front. That's going to make your calculus in this respect a whole lot easier. So there we go. We've cleaned it up as much as we can. We did a bunch of algebra. We did these log properties. Now we do the differentiation. Now, this I know, the derivative of that is 1 over x. So if the derivative of ln of x is 1 over x, what's the derivative of 2 of them? Well, that's 2 times 1 over x, or 2 over x. So I get stuff like this. And then derivative of ln of sine, well, it's 1 over stuff, 1 over sine, times stuff prime, which is cosine. Keep your coefficient 1/2 right here. And then derivative of ln, 1 over stuff times stuff prime. Derivative of that is 0. Derivative of x is 1. So times 1 if you insist, but times 1 doesn't change the answer. Now, I don't know if this freaks you out or not, but this right here, you might say, wait a minute, this is multiplication. My teacher explicitly told me, or expressively told me, that when you have multiplication and you're deriving, you have to product rule. Okay, let's product rule. I'm going to call that F. I'm going to call that G. And if you remember, via your product rule, when you're deriving with respect to x, F times G, that's FG plus FG, prime the first, prime the second. So if 2 is my F, F prime is 0. G, I really could care less what it is because it is ln x here, but that's going to make 0 anyway. F is 2. And then my G prime, the derivative of ln x is 1 over x. So what do I get? 2 times 1 over x, the same thing I got there, which is in effect 2 over x. So when you're multiplying just by a constant here, like if this would have been like a 2x here, yes, I must do the product rule here, but it doesn't have to be that hard. It's just a coefficient, I bring it down, and then I derive the ln. So then 2 times 1 over x is 2 over x. 1 over sine times cosine is cosine over sine minus this. If you wish to distribute, you certainly may. If you'd rather not, the only thing I would do is, remember we talked about sine over cosine being tangent? So cosine over sine is really cotangent. And there you go. We took something absolutely brutal looking, broke it down algebraically with a few log properties, made the differentiation really easy and no big deal. Let's make it a big deal. You say, oh no, that's no big deal. I'm going to do it just like last time. I'm going to use the log properties. One problem with that. This doesn't have any logs. And I say, oh. So rather than think of it like this, say, oh my God, I have to use logs. On a problem like this, and like last one, it's like, I'm thanking the good Lord above that I can have logs to simplify it down. So you say, well, what do I do here if it doesn't have logs? I make it have logs. Again, I can do whatever I want to this side, and what I want to do to that side is to take the natural log of it, so long as I do the same thing to the other side. Again, it's a property of equality. Whatever you do to one side, you do to the other. So it didn't have logs. I made it have logs. And then again, your first property of logs, 1 log with multiplication becomes 2 logs with addition. What happens when I divide logs? I subtract. So I get something like this. Again, no calculus yet. Nothing has been derived. I just want to clean this up algebraically first, put it in as simple of a term as I can get, and then I derive. Now again, power raised to a power. I'm going to pull all these powers to the front. And once we do that, then we can go ahead and take a look at these derivatives. So ln of y equals 2 ln x plus 1/3 ln of 7x minus 14 minus 4 ln 1 plus x squared quantity. So now we derive. How do I derive ln? 1 over stuff times stuff prime. So I get 1 over y times y prime. Bring down your coefficient. Derive ln x, 1 over x. Bring down your coefficient. Derive ln 7x minus 14, 1 over stuff times stuff prime. Bring down your coefficient, negative 4, 1 over stuff times stuff prime. Okay, so that's really the only calculus step in the whole deal. It's just a whole bunch of algebra to do prior to that differentiation. And then let's clean these up a little bit. So 2 times 1 over x is 2 over x. 1/3 times the other quantity is this. Negative 4 times 2x makes negative 8. And then over that. Now, I don't want to spend the time making common denominators here. I think I'd rather, I don't know, hit myself with a hammer for an hour, which is not a good thing to do. I do not recommend you do that. It's not a good time. Not that I've ever done it before, but my goal is to find y prime, to differentiate. So I don't need the common denominator stuff. I just want to get y prime by itself. So how do I do that? Well, I multiply both sides by y. That'll give me 1 times y prime, or just y prime. It'll isolate it by itself. Now, the only thing I'm going to caution you about is here. This y. I'm not going to leave my answer in terms of y. Remember, what was it that y equaled way back at the beginning? Oh, it was that mess. So I'm going to replace y with that mess. So I get something like that. Again, You could not pay me enough money to make common denominators on that. Just walk away. Just let it be. Okay? Ugly, yes. Workable? Sure. Okay, let's try a couple more here. Example 11. Again, I'm deriving the transcendental function natural log. And remember, this is 1 over stuff times stuff prime. So it's 1 over, my stuff is cotangent x. My stuff prime, the derivative of cotangent, is the negative cosecant squared of x. Now, to kind of clean this up, I'm going to do this. When I think about 1 over cotangent, I'm thinking of the reciprocal of the cotangent, which I know from pre-cal is just tangent x. Now, cosecant over 1, or cosecant squared over 1 is just cosecant squared, which I hope you remember is simply the reciprocal of the sine. And then since this was negative, I am going to keep my negative sign. So then next step, I'm just going to write this in terms of sines and cosines. So this sine cancels with one of those. Oops, that would be sine over cosine. Let me try that again. So I get negative 1 over cos x sine x. That is a perfectly acceptable answer. If you insist and wish to separate them, I could write this as negative 1 over cosine times 1 over sine. Reciprocal of cosine is the secant, so that would give me negative secant x times cosecant x. You are free to write it like this. You're actually free to just leave it as is too, in terms of sines and cosines, and that's fine too. Okay, let's do something freaky with this one. This one looks kind of weird. So I want you to think of this as like an f of a g of x. That's really what I got going on here. My outer function is ln. My inner function is ln x. So what do? Well, via chain rule, if I'm going to derive that, remember that's f prime, leave your g, times your g prime. So how do I derive my f or find one derivative of ln? I take 1 over something. Well, what's my something? My something is my stuff, remember? 1 over stuff, or 1 over ln x, times, so we did that part. We did f prime of g. Now I got to derive g. Now I do my stuff prime. And what was the derivative of ln of x? Well, it was 1 over x. And technically, if you want to derive the x separately as a third chain rule factor, an f of a g of an h, you could do that. But so basically I get 1 over ln x times x. Please don't write that as 1 over ln x squared. I would prefer, and I'm sure your Cal teacher would prefer, that you wrote it like that. Okay. Last thing, again, before we go, I want to make sure you got this down. Deriving e to the stuff times stuff prime. I'm going to leave you with these 6 and play with them for a while. Pause the video if you want practice, and then we'll go over them. Okay, I'm going to assume you're done pausing. If not, just work through with me. Remember, differentiating e to the stuff is just e to the stuff times your stuff prime. So my stuff prime here is 5 times e to the stuff. Nothing to this transcendental differentiations. Again, e to the 12x derivative, e to the stuff, times prime of your stuff, 12. This one, e to the stuff, times your prime of your stuff. Now, again, if you want this negative power, you could actually move it to the bottom and say that's negative 4 over e to the 4x, if that gives you pleasure. If the negative exponents don't bother you or your instructor, negative 4 e to the negative 4x is fine. Free response on the AP test, leave it like this. Okay. Here, e to the stuff times stuff prime, if I derive with my power rule there. Again, if you find it essential to move the negative exponent to the bottom, do it, don't do it, your choice. Or your instructor's choice, I guess. They'll be the one that grades your work. Again, this one's a little tougher in that I have e to my stuff, but I also had the coefficient negative 4, and then I multiply by my stuff prime, which is negative 35x to the 4th. So when I put it all together, negative 35 times negative 4 is a positive 140, x to the 4th, and then I get, well, e to all that nasty, ugly, whatever stuff right there. Again, if you wish to move the negative power to the bottom, you can. I'm not going to show it again. I've already shown you a couple times here. This last one, I know my answer is going to be e to the stuff. And then I know I'm going to have to multiply by my stuff prime. Let's talk about that, shall we? One way to find my stuff prime, or the derivative with respect to x, of square root of x, is to say, well, that's the same as deriving with respect to x to the half, and doing your product rule, or I'm sorry, your power rule, stuff like that. My hope is that this is one of those little innate facts that you just have memorized. For instance, if someone were to come up and ask me, what is the derivative of root x? I would tell you it's 1 over 2 root x. If you say, no way. Sure. Power rule. Move the half to the front. Keep your x. Subtract a power. Half minus 1 is negative half. That makes, not that. That makes your 1/2 right here. And then x to the negative half is going to move your x to the half to the bottom. And what does that make? 1 over 2 root x. So technically, I would probably write my answer like this. E to the root x over 2 root x. If having the root on the bottom bugs you and you say I must rationalize by multiplying by root x over root x, in which case you would get root x times e to the root x over 2x. You can do that if you want to. If it's a free response on your AP, leave the roots alone. It's no big problem. And it may be actually on a multiple choice test where it's just the root is left alone on the bottom without rationalizing. So I hope this helps, and I hope that this whole deriving transcendentals isn't so bad as what you may have thought in the beginning. Enjoy.